Greetings. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Today, we hear about biomimetic design, some of the ways that nature's organisms are inspiring modern engineering and architecture. Our guest is Mateus Fernandes, a PhD student in applied mathematics with a Master's of Science in Computational Science and Engineering at Harvard University. We're going to focus today on one of his research projects involving bio-inspired materials, specifically the skeletal structure of a modest sea sponge known as the Venus flower basket. Matt Fernandes and his colleagues have shown that the glass sponge's unique structure is an ideal model for some next generation architecture and engineering designs, and the discovery is attracting considerable attention. And now we'll learn why. We're very pleased to welcome Matt Fernandes. Welcome, Matt.
Thank you so much for having me.
And I would like to ask you, if you would, to give us a little background about biomimetics or bio-inspired engineering. What draws your attention to this as in engineering and so on?
So our approach to this has been more of a collaborative approach.
Yes.
We have been working with a lot of different people with very different backgrounds. And that has been kind of the synergy of what has happened here. The diversity in thought and diversity in being able to think through problems is what really gave us the idea. So biologists came with this idea and this structure to engineers such as me. And we basically looked at it in the eyes of a scope of a structure. And we clearly saw that they had something, they had something invaluable there, something no one had ever seen before. So we started looking into what could be the potential functional significance of such thing. And in biomimetics, that is essentially what we do, right? We look
Right.
we look at nature for inspiration. It doesn't always have the solution to our problems, but it does have a start to really understanding what is that we can use from it to make better structures, better engineering applications, right?
Right. Can you give us an idea of why some of these natural adaptations, you're going to be talking about a skeletal structure, then why some of those adaptations are superior to man-made materials and structures? And can you just give us an idea of what nature is so good about there?
So nature is really good about solving its own problems, right? Sometimes those problems align with our own problems.
Mm-hmm.
And when that does occur, then we can make this as a starting point. Again, it doesn't have the answers. It has a place for us to start thinking about where to improve our modern design. So we can take, for instance, what we took as the skeletal system of the sponge and really analyze what is it trying to do. And from there, we can try to come up with design rules using really our own thought to really expand on that and come up with something that becomes useful.
Right. I'm going to ask you about that just in 1 second, like how you do that kind of testing and with that sponge that you're going to talk about. But I just want to insert that there's a long list of little creatures with minimal or no brains that have come up with wonderful structures, and that has included things like termite mounds for self-cooling and heating, and bird wings for airplanes, and the burrs that inspired Velcro. And now we'll go to this unique little creature, this glass sponge, and you're going to tell us about that, if you will, and then how you get into this, how you determine whether that is of value or not. So could you tell us about the glass sponge and then how you test its particular features for your engineering?
Yeah, sure. So the glass sponges, they live in a very rough kind of environment in the deep sea. And there are many factors that really cause it to evolve in a certain way. So the evolution through many, many years, millions and millions of years, have allowed it to adapt to its environment and provide something that for them is excellent, right? But however, these things have multifunction, right? So the most biological species are trying to achieve a multifunctional
Yeah.
um, task.
Right.
So there sometimes most of these multifunctional tasks align in a way that one is focused, and if that happens, that when that happens, we can actually, and it aligns with one of the applications that engineers are trying to do, then we can actually make use of what we learned from a biological species such as a sponge.
Okay, then could we have a look at that glass sponge and why that is so inspiring? It looks like that is quite something. That's better than the images. Can you hold that up a little bit?
Yes.
Yeah, that's actually, it's quite large and it lives very deep in the sea. And I'm not sure, we'll insert an image too to show that the particular structure really well, but people can see what this looks like. And I believe that structure is designed by nature to trap little tiny shrimp that will be used to help out this creature. So it's quite an interesting thing, a number of features about it. Okay, so there it is, that nice thing. And thank you so much for showing it, because from images, it looks like it's really just a little thing, but actually it's got quite a bit of size.
Well, they vary in size, right, depending on their
Uh,
environment as well. Um,
okay.
I would say this is probably on average, but yeah, so they do. I mean, they have this unique lattice structure,
Right.
right?
Okay.
And they're actually multi-hierarchical. So there's a large hierarchical structure to the skeleton that ranges from its spicules, which is what really constitutes the main frame of the actual skeleton, all the way to the material level of the glass. And people have studied that in great detail.
Yeah.
And one of the research, the scale that we're focused on is the structural scale in terms of the geometry, and it's superb. It's been excellent at discovering how to really distribute loads and the ability to really constrain its deformation so that it doesn't, what we call buckling, so it doesn't buckle when it's under different loads. If it were to have buckling, these species would actually shatter, because glass can't really take buckling, right? Because it's a very brittle material. So it's really trying to do that in a sense. And there have also been other studies shown that in the individual level, the spicules on the individual level are very resistant to buckling as well. So it's a multi-hierarchical thing, and
Yes.
it's fascinating in every level. And people have studied it in great detail, not only for its application, but really just also for understanding of the species.
Yes. Could you, with the engineering and mathematical approach there, can you tell us like how you go about investigating its properties, and then how you model or test to see if that structure will really help? We can't see the actual structure so well from that creature, but if you have an image or we can insert one, right? It's hard to see the structure from there,
Yeah,
but
yeah.
we can insert an image or that shows it. How is that structure when you talk about that being so superior, and what you use that structure for, and how do you go about investigating that?
So to investigate it, to answer your first question about investigating, um, essentially we saw that, well, how did this all come about, right? How did we really even figure this out? The first question was, why is it there? Why is it the way it is? We see it with our eyes, and we really just got to stop and think, like, what does it look like? What does it look like intuitively? What is its purpose? And the resemblance of the structure to modern engineering structures, but really got us to think about it, right? So we took a step back and looked at how we build buildings, how we build bridges with these truss systems, right? Called Tom truss systems, which have been around since the 1800s and haven't really changed much. And we look at them and we realize that they look very close. They look very similar to one another. And we can then break down to its design components, right? We can look at it and then we can do some image correlation analysis to see what is it trying to do? What is the average, right? Because there's some uncertainty as well. Because at the end of the day, it's biological species and there's a lot of statistics that has to be involved. So we look at it statistically and see what is the average trying to do, right? Because a lot of times it doesn't achieve what it wants to do. And the average is this. And this is what we start working with. And then what we do is we build computer simulations using finite element analysis. And that's basically a mathematical description of mechanical deformation. So we use that to discretize, to really chop it into pieces, like not chop it into pieces, but like analyze it into small pieces. And using that, we can then see what is the deformation, what is its strength, and what loading condition. If we were to try to do this in experiments, we would take probably many, many years to do because we would have to build, we'd have to 3D print each one of these specimens to really understand how it's performing, right? So instead, to really save time and be able to do it efficiently, we do computer simulations. And it's shown in simulations that it's really good. So we compare that to existing structures and we compare it to obviously no diagonal. So this, and then once we do that, we validate it with the experiments. Essentially, we 3D print these structures and then test it in a compression device.
Okay, so there is a way to actually test it. You can't run out and build a big bridge or a skyscraper to say that's a test. It's just a test. So you work it out mathematically, you test it with some kind of modeling, and that's pretty reliable, I take it, right?
Yeah, so we match the simulations very closely. Again, it's a validation, right? Because the simulations can be very complex. So it's prone to mistakes. And so the way we really test for mistakes is by creating by creating experiments. And that the game changer for that, and the reason this hasn't been done, is technology. We've been able to come, very long ways in 3D printing technology that has enabled us to really that has enabled us to 3D print these structures in a very uniform way, in a very isotropic way, which means like the material is very good, right? Because or else you'd be looking at the material and the fact that the printers are not good. And so instead now, because of 3D printing is so well, we can actually do testing on these structures and get reliable results.
Okay. I want to get a clarification here. First, the structure itself, we were not seeing that at the moment, but it's a lattice structure, you say. And as I said, we'll insert the image. But for those of us who are not engineers, you use a term in engineering, strength to weight ratio, meaning that that structure, it can support much taller buildings and it's much stronger for certain types of bridges, like very long bridges or something, I think. In any case, what does that mean, strength to weight?
Right, that's a great question. So strength to weight ratio is essentially giving you a metric on how efficient a structure is. So you can always have a very strong structure if you make the strength to weight ratio, if you have that weight very high, right? So you put a lot of weight. So you're basically just getting the material, a big solid block of, steel, for instance, right? So you're getting good strength, but what is that good for? Yes. You can't, like if you were to build a bridge out of a solid block of steel, that would be kind of useless because you couldn't really drive very far, right? Because you'd be going into like a big block of steel. So instead, what you do is you arrange the material in a very efficient way. And that was done by Ethel with wood back in the day, in 1800s, and he invented and patented that. He was an architect in Connecticut, and so he patented that lattice design that was, when it's this first high strength to weight ratio, meaning that you have little material and still have strength. So you're essentially just putting material where it's necessary, where it gives the structure strength, rather than having redundant material do nothing. So, but that was more intuitive. There was not much, there was not much simulations put into that. It was all done by him, drawing it out and kind of solving some geometric equations, which is great. But he is always kind of constrained into having basically one diagonal, and so have people. And it's always been thought of that it's inefficient to add more diagonals because it doesn't really improve this strength to weight ratio. People really haven't really thought of it in the way that the sponge has introduced this kind of unintuitive result. So this is really what has led to this increased in strength to weight ratio, is by adding this other diagonal, we're actually not adding more material to the structure. We're keeping the structure the same amount of material, and therefore we're increasing its strength. So as a result, the weight's the same and the strength is higher. So we're actually increasing the strength to weight ratio.
That's very interesting. So the sponge's skeleton offers just another diagonal in that lattice structure, and that alone increases the strength, the ability to hold or stabilize loads much more efficiently. Is that correct?
That is correct.
Okay.
Actually, it's not just introducing another diagonal. It's introducing another diagonal and offsetting them, so that you really you have to have it actually in the right placement. And so we also did so then that begs the question, well, is this still optimal, right? And that is what we answered. We then created an optimization algorithm to analyze different cases. So we kept adding diagonals. So the first one, we had one diagonal, and we actually optimized how much material you allocate to the diagonals versus the non-diagonals. And we tuned that and really run a lot of simulations, right? If we were to do that in experiments, we would probably last a lifetime of experiments, so we would never get results. So once we trust our simulations, then we can really, once we validate the simulations, we can trust them, and then we can actually do these optimization algorithms to really analyze, all right, now if you add another diagonal, what if it's 3 diagonals, right? What is 4 diagonals? What is it 5? What if it's 6? And then where do you place them, right? Because you can place them anywhere. So, and the optimization algorithm, what it does is it looks at different placements and different number of diagonals to see what is the best combination that gives you the highest strength to weight ratio.
Yeah.
And we are very close. The sponge is not optimal. Again, it's not optimal because it has other functionalities. It's trying to feed, who knows what the functionalities.
It's not holding up the buildings.
Yeah, right, exactly, right? So it's never intended to hold up buildings. So, but it gave us the starting point to develop the optimization algorithm. But to be honest, it's actually very close to the optimal. Yeah. And it's 2 diagonals, that's solved. If I add 3, if I add 4, if I add 5, we lose that strength to weight ratio quite fast. If we go 1, we still don't have that, right? So you have that optimum point at the 2. But then how do you allocate material to the diagonals? It's still very close. The sponge does very well, but it's not quite optimal. And then the placement of it's also very, very close, which is very remarkable for a biological function like this.
Yes, that is really fascinating. I didn't realize this is a lot of modeling work, evidently, or a lot of mathematical work on your end. This is not something you do in a couple of days, evidently.
No, you have to really test it, right?
Yes.
Because it's a hypothesis.
Yes.
You come up with a hypothesis and you really want to prove, or just, you want to try not to disprove the hypothesis. And how do you do that? Is through testing. Lots of testing. And so that's what we did.
I see.
And lots of simulations.
Yeah. Matt, just a curiosity, when they develop these span bridges and this sort of thing and use these sort of the basis of this kind of strength to weight ratio, they didn't have modeling systems, right? They didn't have algorithms. They didn't have computerized testing and stuff. Is that correct? So does that help you?
Yeah. So indeed, yes. And so span bridges, if I'm not correct, I don't think span bridges are the cable bridges, right? They're not the.
Yes. Yeah.
So they don't use this.
Okay.
So these are more like so if you live in Boston,
Yes, our
you'll
famous
know.
bridges. Yeah.
Yeah. So you'll know
Ones.
the Tobin Bridge. The Tobin Bridge very famously has these diagonals. They're not like the Zakim Bridge with the cables.
Yes.
And Zakim Bridge is a very different design and
Got
does
it.
not involve any lattices. It does involve tension, but it does not involve lattices. But
Right.
the Tobin Bridge, on the other hand, is fully made by lattices. So when you drive through that green bridge, you will really look closely at it. You'll see the multiple hierarchies even
Yes.
on the lattice of the bridge, and that is based off of the town trust system, and that has it's worked great. But is it the best? Maybe not,
Right.
but it's great. But can we
Yes.
increase efficiency? Perhaps we could. New bridges. I'm not saying we need to tear down bridges. These bridges are great. They're working perfectly. I think what we can do is maybe in the future build more efficient bridges, waste less material, or perhaps make it longer, right? And buildings are we're reaching a capacity on how tall we can build them.
Yes.
And so can we actually build them taller as a result of something like this? Because as you're increasing the strength to weight ratio, you're enabling the ability to have less weight on a building and still have more strength. So that allows you to build it taller, right? Because it's compounding over the length of the building.
Okay.
So the taller you build a building, the bottom will feel more and more and more and more weight. So if we can reduce the weight up top of the building by using a higher strength to weight ratio structure at the top, then we're actually really lowering the amount of weight at the bottom also. So by improving the strength to weight ratio on a lattice of a building, you're actually not just having a small effect on the building itself. You're compounding that over the length over the height of the building,
I
almost
see.
like interest rate, right? As you go, each increment actually really makes a big difference.
Right. It sounds very exciting, Matt. But in terms of, you mentioned this gives you like an optimal structure here. Do you have to so just in terms of the geometry, do you have to change materials? Does that make a difference? I don't know if that's your field.
So absolutely. The optimality here is the asterisk, right? It's
Right.
one thing we considered, and that was inspired of sponge. There are other structures, right? So this is the design space we chose,
Yeah.
and this design space, the sponge is very close to optimal design space, which is better than other structures. But there could be others, right? We could find other structures somewhere else that will introduce even better, right?
Yeah.
We don't know. This is limited by our creativity and the ability to really think outside the box like these species have. So again, we may be inspired elsewhere to even consider another design that can even provide a better structure. So optimal, yes, optimal within the design frame that we're looking at, not necessarily everywhere, right? So
Right.
there is still a possibility, or I would say a high likelihood of there even being a better structure out there.
I see. That's the structural part of it. How in
Material.
material, do you have to alter that or
So
looking at that?
no, so the material, and that's a great question as well. So what we've learned from the sponge is not material dependent. It's a geometrical thing.
Yeah.
So it's a geometrical distribution of material, and it does not really depend on the material. However, the material does impact how much the material itself could fail, right? There are two
Right.
types of failure. You can have this kind of structural level failure, or you can have a material failure. And
I
if the
see.
material fails, so if it's made of paper,
Yeah.
You know, it doesn't, right? It doesn't matter what the paper is
Exactly.
gonna rip first, right?
Yes.
It has to be, the material itself obviously has to have a threshold. The threshold that is currently with bridges, right, that we use, steel, galvanized steel, or whatever steel we use, would still apply here, because we actually see relatively the same stress distribution as in current geometry. So we're not increasing the stress. However, we're increasing the ability of its being able to handle load before the actual geometry fails. So once you hit this threshold, then it's material independent.
Okay.
It's a geometrical artifact, and it's a geometrical way of looking at the structure.
I see. Got it. Now, then this is very exciting. And I would like to shift a little bit to anything you're working on. You haven't even gotten your PhD yet. You're already in Nature magazine and all sorts of publicity, which is just great. Of course, the organizations within Harvard that you're working with they produce something about every week that hits the news. So that's a good place to be. But can you tell us about your other interests or some other interests that you are developing?
Absolutely. So we're in terms of research, we're working on very different things. My group is very unique in the sense that we're super collaborative, and that is really our strength. We work in very different fields.
Multidisciplines, you mean?
Multidisciplinary, yes,
Thank you.
exactly.
Okay. Mm-hmm.
And it's primarily why I chose to come here. On my admissions essay to Harvard, I actually wrote, I started my essay as, I want to be a super engineer. And because, but what does that, how is that defined? It's defined as one that really has a skill set that can be carried over to different disciplines.
Mm-hmm.
And really innovation happens at those intersections of different disciplines, right? Because that's what has not been explored. And there's so many combinations of different disciplines that you can use, that you can really find anything anywhere and really have a high impact. So at the end of the day, what we're working on now is also to extend this project. And we're looking at different level of hierarchy of the sponge and really analyzing another level of hierarchy. So I'll let you stay tuned for that. But the other thing that I'm working on is looking at something called negative Poisson's ratio, and the ability to use that's called an auxetic material. So essentially what that does is when you compress it, it shrinks. So, right. So when you think of a normal material, when you compress it, right, when you compress something, it tries to bulge up, right? And when you pull on it, it tries to thin out, right? So negative, that's a normal Poisson's ratio. The Poisson's ratio is a ratio that essentially correlates how much this shrinkage is when you pull, and how much this expanding is when you compress. So imagine a material that when you compress, it actually shrinks. When you pull, it actually gets bigger, right? So we're looking, and that's called auxeticity, auxetic material, which basically means that it has an effect that is unintuitive, right? So what we're looking at is using these auxetic materials at a different way. These have been explored very well, and we're looking at it in a way to introduce another design parameter to be able to control friction. So can we use these materials to control friction or even control light scattering? And that's something else that I'm looking at as well.
Wow. You bring up this multidiscipline approach here where people from different specialities get together, put their heads together, and come up with incredible ideas. In terms of development, so you do this groundwork stuff. Does this work? How to make these kinds of innovations work? And then how long does it take to get something actually what would we say, to market? I can't think of another phrase for it, but actually in use, like the structure of the lattice structure, applying that to buildings and so on. How long does that take?
That's a great question.
A
It
sad one.
depends. It depends. Well, no, it could be very fast. It depends on how established the field is.
I
For
see.
instance, the field of art, building and architecture, it's almost like the field of, aircrafts, because it's so established and it's worked for so long, and there's so much risk involved and change that at the end of the day, it takes a lot longer. So, for instance, for our structure, we're going through the commercialization side of this. It's obviously patented and all that, patent pending, but we're trying to come up with different strategic partners to make it work. And we're making headway on that. But at the end of the day, there's a lot of testing that needs to be done to validate, beyond what I've done, but to validate its safety, because there's so much at risk in structures like these that you do not want to make a mistake.
Exactly.
So, and obviously, anything can lead to a mistake. So it's very important to do very careful testing at every level, right? And at the end of the day, even have a full prototype of it and do a test on it to be able to have something that actually works and that we can trust, because we do not want to compromise any safety at any level. And because where these structures go, there's a lot at stake. There's a lot of testing that needs to be done, and we're doing those.
So it might take, would we say, years before you say you develop something, you've got a good idea, you get a patent to protect your work, but then you look for people to collaborate with to get it into a product mode, an actual product mode, right? And this can take some time. Give us an estimate for using this structure that you've tested now.
Yeah, so the way I see it is the research phase and there's development phase, right?
Yes.
So the research phase is we don't know what we're doing, right? And then the development phase, we know what we're doing, and now we're trying to achieve something very specific. The research phase can take, 2-3 years. And in the development phase, I would say there's another 3 to probably 5, if not more, depending on the field, years. So we're at this second part now, and we're a few years in, and we're really trying to make headway on trying to get this out and useful, right? We really want to have an impact on the world.
Right. There's a real need for this kind of structure. Would give you a lot more options, I suppose, many more options in terms of bridges and buildings, things that you can do. And I think it sounds wonderful. It's certainly, in some ways, an uphill process, but we thank that little sponge. It has contributed a number of characteristics that people are interested in, that silica, all sorts of things that are of great interest, and the structure. And Matt, I just wish you all the best. It sounds like you're going to have a brilliant career, and it starts so early. It's just an amazing thing. But I wish you the very best of luck. And thank you so much for joining us today.
Well, thank you for having me. My pleasure.
Okay, thanks.